class. Today we're going to be doing section 7.25b, which is a continuation of our chi-squared tests, our hypothesis tests and confidence intervals for AP Stats. So in the last lesson, we went over the chi-squared goodness of fit test. Today we're going to be looking at the chi-squared test for homogeneity. So for our first example, medical researchers enlisted 90 subjects diagnosed with depression for an experiment comparing treatments. The subjects were randomly divided into 3 groups and given pills to take for a period of 3 months. So I'm just going to kind of circle or underline things that I think are going to be useful when I start doing my test here. So we have randomly divided into, and we have 3 groups. Unknown to them, one group received a placebo, the second group, so unknown to them means it was blinded in that aspect. Second group, the natural St. John's wort, and the third group has the prescription drug Post-Rex. After 6 months, psychologists and physicians who did not know which treatment each person had received, so it's a double blind, evaluated the subjects to see if their depression symptoms improved. So we want to know if symptoms improved. Table below summarizes the results. So we've got 3 different treatments, and we have information for how many people said that there was no change in their symptoms and how many people said that their depression symptoms improved within each one of the treatments. Researchers wanted to determine if the rate of success or failure is the same for all 3 treatments. 30 out of 90 patients reported an improvement in their depression symptoms. Okay, so if I take, so this is total of 30. Okay, and then it says, while the remaining 60 reported no change. So this has a total of 60. Fill in the expected values. So if we were expecting to see the same amount for each one of the treatments, then if there was a total of 30 people who said depression symptoms improved, we would have expected to see 10 here, 10 here, and 10 here. And out of the 60 people, we would have expected to see 20, 20, and 20 if it was all the same. Now, sometimes in this case, it was pretty easy to figure out what the expected values were. Sometimes it's a little bit more difficult. So we can actually use our calculator to help us find these expected counts for chi-squared test for homogeneity. So if you look at, we don't just have one list of values, and we don't have 2 separate lists like we've seen before. This is one group of people, 60 people reported no change in depression symptoms, while 30 reported that their depression symptoms improved. So with these types of problems, we need to use a matrix. If you've never used matrices before, they're pretty darn cool. So if you hit second and then this button in your calculator here, we can get into the matrix. And if we go over to edit and hit enter, and I've already filled this in, but I'll explain to you here how to do that. So go to edit, hit enter, and then this is going to be the number of rows by the number of columns. So I have 2 rows and 3 columns. And then you can just kind of keep hitting the arrow button, or you can hit the enter button, and it'll cycle through these and you can type them in. Now, to figure out, if you couldn't figure out the expected values for the counts on your own manually, we can actually have the calculator do that for us. So once we get those observed counts in there, we can go to stat and then tests and then all the way down to chi-squared test. Now, if you look at chi-squared goodness of fit test, it asks me for lists. I don't have lists. So, oops, I just want stat, tests. So if I go to the other chi-squared test, it asks me for a matrix. So that kind of reminds you like which one is what. I put my observed counts in matrix A. I did not put observed or expected counts in matrix B, but what this is going to do is if I tell it to put the expected in matrix B, it'll do it for me. So then I go to calculate, and we'll use these in a second, but what I want to show you now is if you go, hopefully you're doing this with me, if you go back to the matrix, so second matrix, and you go down to B and you hit enter, it's going to give you the expected counts. And those are the same ones we found by hand. So it's really nice. I did not put these values in there. The calculator just does it for you once you run that chi-squared test for homogeneity. And then for showing your work, it's really important that you put all the expected counts into your table. And you can do that by just putting them in parentheses, as you've seen me do it here. Now it says, determine if the treatment results are the same for each group. Explain your reasoning. Well, this kind of question, if we don't do a test, is pretty subjective. You could say, well, there's, I don't know how you would do this, but I would say no. I mean, personally, if you look at the post-recs, we expected 20 of them to say no change in depression symptoms, and 10 of them to say that their depression symptoms improved, but it was actually more people said that they improved than not improved on that drug, which is definitely different than the other two treatments. So you could explain that. I'm not going to write it all, but you could explain something like that. But the problem is answers will vary. This is subjective to whatever, if you're just looking at the numbers and trying to decide, you're kind of basing it off of your opinion with your own inherent biases. So we need to have a formal way to test this process, to see, or a process to test this, to see if it is different or not, without having to just hope that we were guessing right, I guess. So the subjective nature of deciding whether the observed counts of successes or failure between treatment groups significantly differs from each other requires a formal process, statistical inference, on which to base our decision. So a chi-squared goodness of fit test doesn't really work here because it compares the distribution of observed outcomes for a single group with respect to a single categorical variable. We don't have that. We have three groups here. We have three different depression symptoms or depression treatments. We still have a single categorical variable, which is depression symptoms either improved or not. But we have three different groups. So we can't use a chi-squared goodness of fit test. What we're going to use is a chi-squared test for homogeneity. And homogeneity just kind of means sameness. So if you're just testing to see if they're the same, and that's kind of the clue in the problem, whether you should use this or not, and the number of groups, then we would do it this way. Now, technically, we can test for sameness in goodness of fit test, but that's if we only have one single categorical variable or one group, categorical group. Okay. A chi-squared test for homogeneity compares observed distributions for several groups to each other to see if there is evidence of differences among their respective populations. There are several groups, but only one variable. Now, the goodness of fit test format mostly applies. So the conditions, the equation, that sort of thing, a lot of it's the same. It's just different how we write our hypothesis statements, and it's going to be different when we write our conclusion at the end. But pretty much everything else is about the same between the two. So the null hypothesis, so we just want to say this in words, the null hypothesis for a chi-squared test for homogeneity is always that the categorical counts are the same. And of course, we want to write that in context. So for example, the rate of improvement in depression symptoms are the same for placebo, St. John's wort, and post-rex treatments. And then our alternate would be the opposite of that. So the rate of improvement in depression symptoms are different for the placebo, St. John's wort, and post-rex treatments. Identify the test by name. So this is a chi-squared test for homogeneity. And I know the goodness of fit test, we could write GOF test, but this one, don't abbreviate it, just write it all out. All right, assumptions and conditions are going to be the same. So we need to make sure that our data is counts. So the depression symptom counts are given for each treatment group. We need to make sure that we have a randomization condition. And if you remember in the problem when we read it, I underlined randomly divided into three groups. So this stated that the 90 patients were randomly divided into treatments. Our independence assumption, so we want to look at our sample size. So we had 90 subjects Oh, in 3 groups. So we had 30 subjects in each group. Okay, so this one gets a little tricky. We're not looking at all 90. We need to look at the sample sizes for each group and make sure that they're big enough. So 30 is less than 10%. And we're assuming this. Assume 30 is less than 10% of the population of each treatment. So again, we're looking at each treatment. So there's 30 people here, there were 30 people here, and there were 30 people here. So 30 in each treatment. So, oops, went too far. So assume 30 is less than 10% of the population of each treatment. So independence within each group is assumed. And then because they were randomly assigned, we also, based on randomization, we can assume that each treatment group is independent of the other groups too. It doesn't hurt to write that down as well. All right, sample size assumption within, the expected cell counts are all at least 5. So that's the same thing. Remember, our expected cell counts were 20s across the board and then 10s across the board for our other, for the depression symptoms improving. Our test statistic, which is our chi-squared test statistic, this is the same as before. So the sum of the observed minus the expected squared divided by the expected. So in this case, we would have, so let's go back. We had 24 observed in the first piece minus 20 expected. So 24 minus 20 squared over 20 plus. And then I would go through and do all of those, but we can shorthand it, just do dot, 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 and then do the last one, which is 16 and 10. So 16 minus 10 squared over 10. And then I'm going to go back and rerun my test because I didn't write it down. So go to stat, tests, chi-squared test. I know it doesn't say for homogeneity, but that's the one you want. A and B, and I'm going to calculate this. I have 8.4 for my test statistic. My degrees of freedom are a little different. So it says it's 2. Now, if I just write degrees of freedom equals 2 and I don't show how I got that, it could get me into trouble. So in this case, and I wrote it here, specific to the chi-squared curve, depends on our degrees of freedom. And in this case, it's the number of rows minus 1. So we had 2 rows. So 2 rows minus 1 times the number of columns. We had 3 columns minus 1. So that's 1 times 2, which is 2. You want to show this work. All right, and then I don't think they showed us an alpha level, so we'll get to that in a second. Let's do our p-value. So I want to go back really quick. Instead of hitting calculate, when we do this in our calculate chi-squared test, instead of hitting calculate, we can hit draw. Whoops. I have to turn my plots off. Okay, so if you do this, make sure your plots are off. So all my plots are off. So now let me do this again. So stat, tests, chi-squared test. Let's see if it'll draw it for me this time. There we go. So it's kind of nice. We still see the chi-squared value. We still see the p-value. Notice we've lost the degrees of freedom value. So I do like the calculate, but I wanted to show you this curve. It's very different than a normal distribution or a t distribution. And you can see on our AP stats formula sheet that that chi-squared curve is skewed. It's definitely skewed. So, so this is kind of a different looking curve. And the curve really looks like this, just so you know, but I just wanted to kind of show you that. All right, so our probability. And the other thing we talked about before in our last lesson is that it's always an upper tail test. So the shading is always on the top here. So it's always the probability that your chi-squared value is at least what you get. So at least 8.4. And then I want to show my work. So chi-squared CDF. I'm going to go second and notice my p-value of 0.015. So I'll show you how to get that here while showing our work. So chi-squared CDF. Oh, Well, that's strange. Last time it gave me my inputs. Oops. There it goes. Not sure why it didn't do it for a second. Okay, so our lower value is 8.4. So lower is 8.4. My upper value, just make it some big number here. And then my degrees of freedom is 2. So I need to go down to 2 degrees of freedom, paste, and that's the same probability that we had before, which is 0.015 approximately. All right, and then if we look back at the problem, they did not give us an alpha level, so we can just assume, and I'm going to write it on the next page here for my conclusion. So I'm going to assume that alpha is 0.05 since it wasn't given to me. Since our p-value, so p-value was 0.015, so our p-value is less than or equal to alpha, so that is definitely less than 0.05, we reject H naught. So remember, H naught is that the things are the same. If I'm rejecting that, then we have sufficient evidence to support the claim that the rate of improvement in depression symptoms differs for the placebo, St. John's wort, and post-Rax treatments. So that's kind of the whole chi-squared test for homogeneity that runs through all of it for you. Now, there's one piece that comes up a lot, which is the condition that our expected cell counts are all at least 5. So this one here. So what do we do if our expected cell counts aren't all at least 5? And let's look at an example there. So we'll have an example, but what we do really is we use the cell residuals. So recall that the chi-squared statistic is a summation of the discrepancy between the observed and expected cell counts of each cell. So we need to be careful that cells with small expected counts not be the ones that primarily make the chi-squared statistic large, so that the null hypothesis is rejected. So it's especially concerned when the sample size assumption is not met. So if our expected counts aren't all at least 5, it can kind of weigh heavily on our chi-squared statistic, making it more likely to reject the null hypothesis, and that might lead to an error. So we want to make sure that if we don't have the expected cell counts all at least 5, that we have some way to check to make sure that what we're doing is okay. The cell standardized residual is C equals the observed value minus the expected value divided by the square root of the expected value. So this is actually just the square root of the chi-squared part of the formula. So if we had observed minus expected squared over expected, and I square rooted the whole thing, then I would get this. Standardized residuals can be thought of as z-scores. They're not z-scores, but they can kind of be thought of it. A standardized residual as plus or minus 1.75 is not highly unusual. However, a standardized residual of like 6.75 would be a concern. So we want to make sure that our standardized residuals are not too large or extreme. For example, and now if you're one of my students, this example is actually a full hypothesis test that you'll need to do, but I'm just going to go over the unmet condition, and then so the video is not too long. A geneticist wants to determine if left-hand, right-hand dominance traits are the same across eye color. The table below summarizes hand dominance and eye color for a random sample of 114 adults. What conclusion can the geneticist make at a 0.05 level of significance? Okay, so again, and I didn't preload this yet, so it's going to take me a second. So I need to go to the matrix, here. I'm going to go over to edit, and I'm just going to use I'm just going to go back up to the first one. I'm going to change the size because now we have 4 by 2. Okay, and then I have 6 and 36, 7, 26, 2, 21, 4, and 12. Okay, so then I'm going to go to stat. I'm going to go run my test, even though I know that it's early. We don't need all this information yet, but by running my test, my chi-squared test, it'll put the expected value, expected counts in matrix B for me. So now if I go back into the matrix, now notice B changed. I didn't change it. It was 2 by 3. Now it's 4 by 2. And it's going to give me all of the expected counts. And I'm going to write those in. So the first one, and we're going to use parentheses, is 7. I've got 35 here. So far, so good. 5.5, 27.5. And now we've hit a problem. 3.83 is not at least 5. 19.17. 2.67, again, is not at least 5. And 13.33. So we have an unmet condition. The expected cell counts are not all at least 5. So we need to find the standardized residuals for the 2 values that are not those conditions not met. So the green left-hand dominant and the other left-hand dominant, we want to calculate the residuals. So, so we want the observed minus the expected divided by, where did it go? Oh, there it is. Okay, sorry. Lost it in my notes here. So the observed value, which is 2, minus the expected, 3.83, divided by the square root of the expected, 3.83. If you plug that in your calculator, you get negative 0.936. So if we think about it being only less than 1 standard residual away, so kind of like think about z-scores, less than 1 standard deviation away isn't too far. It's not extreme. So that's fine. These are not the same as z-scores, however. And then other, so we've got 4 minus 2.67 divided by the square root of 2.67. And when you plug that in, we get 0.816. Again, not extreme. So these residuals are not extreme. So we may proceed with our test. And this is how you would write it after saying that, oh, our expected cell counts are not all at least 5 in that condition when we're doing our conditions for the test. Now we can keep proceeding with our test and we can run the rest of it. All right, and so if you're one of my students, make sure you do the rest of this problem. And that is it for today's lesson.